Hello and welcome back. We just started a section on duals and double duals, and after introducing the so-called dual transformation, we are now investigating another very important transformation, which is the canonical map. The canonical map allows you to go from a given normed linear space X to the bidual of X. It was defined in the rule that is written up here. So whenever you have a point X in X, the action of Jx, which is an element in the double dual or the bidual, is just pointwise evaluation of the functional at the given vector x, okay, for all f in the dual space. And that in turn defines a mapping between x and the bidual by sending the vector to this element in the bidual j sub x. All right, as it will turn out, that map is very important. That's why it has a name, canonical map. Now we started gathering some properties of the canonical map. So first off here, in general, if you have a normed linear space, then that capital J, the canonical map, is a bounded linear transformation, and moreover it preserves the norm, so it's an isometry. This we already proved, that used the definition for one direction and then the for the linearity and for the norm estimate in one direction, and then again Hahn-Banach for the other direction. Once you had established that it's an isometry, then you get for free that it's injective, because all isometries are injective. And now we have to still establish here the last part, that is, if that normed linear space is complete, so a Banach space, then the range is a closed subspace of the bidual. And that's a special thing, because typically that's not going to happen to your arbitrary bounded linear transformation. The ranges are in general not closed. Whenever that happens, then you're dealing with something special, and the canonical map is special. So that's why we gather that property here. Now to prove it. Right, so as we're saying, this we already did. This is about the linearity and the isometry. Yeah, the first inequality here, that's the trivial one, just playing around with the operator norms and basic estimates. And then the second one, that uses Hahn-Banach. It's up here, and we get the isometry. All right, so now after this it remains to establish that in a Banach space the canonical map is, well, the canonical map has a closed range, right? That's what I'm trying to prove. All right, so now assume X is a Banach space, and so how do you show that something is closed? Well, you take a convergent sequence in that set, and then you show that the limit is again in the set, right? Then it's closed. So let's take a sequence in the range of the canonical map. Well, remember the range of the canonical map, those are all those j sub x, right? So now I take a sequence in there, so that will be a sequence j sub xn, right? This will be a sequence in the range, all right, where xn is a corresponding sequence in x, and let this one be a convergent sequence in range j. Say jxn goes to, well, k, some element in the bidual, as n goes to infinity. Okay, now to show that the range is closed, what we have to establish now is what I write here in yellow, that, well, that there is some, say, element x infinity, that k is equal to jx infinity. All right. And of course, how will you do this? We will investigate convergence properties of the sequence xn. If we can establish that that guy is Cauchy, then, because we're working in a Banach space, we will have a limit x infinity, and that limit then will be lifted under the canonical map to the corresponding limit here, j sub x infinity. That's the strategy. All right. So to execute it, it's not hard. So then, for all linear functionals and any natural numbers n and m. So what I'm going to estimate here is f xn minus xm. Okay, since you're dealing with a linear functional, you can split up the action on that difference there in this way. And now you need to remember how that little map J was defined. So this is, the first one is J sub xnf, the second one correspondingly or accordingly J sub xm of f. Then you use how, well, you add two linear maps, right? Because after all, that J sub something is a linear functional on the dual, right? It's an element in the bidual, so it's a linear map in particular. So that thing here is defined pointwise. Okay, and then you do the usual trick. You estimate the operators here like this, like how we have done it multiple times. Okay, so you have this. Now you know already you have control over this guy because of the assumed convergence of the sequence J sub xn, right? So this guy here, J sub xn minus J sub xm, in operator norm you can make as small as possible for nm large. So now how you can conclude from that then the xn and xm in norm are sufficiently close, well, and thus this will be an exercise. So the exercise I will write here in yellow. So as it turns out, once you have the Hahn-Banach theorem, you can compute the norm of a vector, say here, okay, I have indexed my space, so with x, you can compute it by this formula, right? That's a very, very short exercise. It uses Hahn-Banach theorem, and you will do it in the exercises. So this is what I'm going to use now. So what I'm doing here now is I will start here on the left, this one, and remember this estimate is valid for any linear functional on x. So I will optimize the inequality over those linear functionals that have operator norm equal to 1. Right, so and then what you get is on the left, well, on the left this will be precisely the norm of the difference xn minus xm. So xn and minus xm, and then on the right you will have at most, well, jxn minus jxm, right? Because you optimize over linear functionals with norm 1, so here is your 1. Right? So you have this, but this shows then clearly, hence, that xn is Cauchy, as promised, and so since you're working in a Banach space, xn goes to some x infinity as n goes to infinity. Okay, so you got this limit, and that is enough now. However, now we play around a little bit with the triangle inequality and using the fact that the canonical map is an isometry for any n in n, since J is an isometry. Well, I would like to show that J sub x infinity and k are the same, right? Then I would be done. That's what I wrote earlier in yellow when I discussed the strategy. So how can I do this? Well, you use triangle inequality. The left hand side is independent of n. Keep that in mind. And then you have this one. Remember, J sub xn converges to k, so you have immediately control over the second one. That's why I insert that thing with n. And over the first one, remember, by definition of the canonical map, this is capital J x infinity minus capital J xn, right? Yeah, but capital J is an isometry. This we already checked, right? J is an isometry and it is linear, so that first thing is just x infinity minus xn in the norm on x. Okay, and with that little trick now you have control over both, because this one here also goes to 0 because our sequence was Cauchy and the x infinity is the limit, right? So now all that remains to do is you push n to infinity. Remember, the left hand side does not depend on n, so it goes to 0, and that means this norm here on the left has to be identically 0, and that shows that j sub x infinity is equal to k, and that's what you need, okay, or that's what you wanted, okay. Hence j, oh, I'll write it the other way around, say k is equal to j x infinity, and this is of course an element in the range of j, and so the range is closed, right? Because that's what's the strategy. Take a sequence which is convergent in the range and then show that the limit, which is this k, is also in there. So it's closed. Right? It has range j is closed. Okay, that is that. J is closed. Good, very nice. Now, we will now gather more properties about biduals, and the first thing has to do with the following important concept. So remember this result in the last section, the last one, that if you have a Banach space and its dual space is separable, then the space itself is separable. This is proof by contradiction via Hahn-Banach. And if you want to make a statement about the other direction, suppose you have a separable Banach space, is the dual space going to be separable? Then this is in general not true, but it is true in the class of Banach spaces that I'm about to define and the ones which we will now study. So a Banach space X is called reflexive. Well, if and only if the range of the canonical map is all of the bidual, right? So in other words, in the reflexive Banach space, the canonical map is an isometric isomorphism, right? Because it is already injective, that we know. Now, putting this constraint on it, that the range is all of the target space, that makes it surjective, that's the only thing which is written here, that the canonical map is surjective in a reflexive Banach space. And then, since you already know that it's an isometry, that combined is enough to conclude that it is invertible. Okay, because remember, invertible means you have bijectivity and the inverse is bounded. But whenever you have the isometry, that property, the non-preserving property, and you have something bijective, then automatically the inverse is bounded. Okay, so in other words, in reflexive Banach spaces, the canonical map is an isometric isomorphism. That's what happens. Okay, good. Now, a few properties about this proposition. So a closed subspace Y of a reflexive Banach space X is reflexive. Okay, so remember, whenever you have closed subsets in complete metric spaces, they are themselves complete. So this closed subspace Y here is itself a Banach space, so it makes sense to ask yourself whether it is reflexive or not, and as it turns out, it is, precisely when the bigger one is also reflexive. All right, that's the first thing. And if you have two isomorphic Banach spaces, so remember that means Banach space X, Banach space Y, and there exists invertible bounded linear transformation between those two guys, then if one is reflexive, the other one is reflexive. So isomorphisms, they preserve reflexivity of Banach spaces, right? And so is any Banach space isomorphic to X. All right. So if you study this reflexivity for the first time, it can get confusing pretty quickly, because you need to juggle all those definitions between canonical maps, duals, biduals. We will also now have triple duals. So it needs some time, but it all works out nicely, and the stuff starts growing on you in time. So first off, let's do this with the subspace. So since Y is a Banach space, all right, we pick linear functional, say k, in the bidual of y, and now needs to show that there exists y, and vector in y, so that this element in the bidual is of the form j sub y, where j sub yf is equal to f of y for every f in y star, right? That's the first thing. So remember, reflexivity means that the canonical map is surjective, right? So that means, that's exactly what I'm writing here. So any element in the bidual, but here everything on the subspace level, so y's instead of x's, is equal to, well, this j sub y, right? Because this is capital J acting on y, right? And that means surjectivity, right, of the canonical map on y, right? And that's sort of paraphrasing what surjectivity, what reflexivity of the subspace means. Okay, so this is our goal. All right, so how do we find this? Well, to this end, you have to go back to the bigger space, because you know in the bigger space things work out nicely for your canonical maps. So to this end, construct, you could call it the lift, because you really lift it to the bigger space. So L of f, which I will take as k. Now k, of course, I would like this to make sense for all linear functionals on the bigger space. Yeah, but k doesn't, make sense there, because k, acts on elements in the bidual of y, not k is an element in the bidual of y, so it acts on linear functionals on y. It doesn't necessarily act on linear functionals on x. Yeah, but this is an easy fix. You can just restrict your input functional to the subspace. So this harpoon to the right upwards, this means the restriction. Okay, I will write it out. So where f, so this is a linear functional on y, denotes the restriction of f to the subspace y, and that is perfectly well defined, because your linear functional acts on all of x, so in particular it acts on the subspace y, okay, to the subspace y. All right, then a few things to be checked, but these are easy. Clearly, L is an element in the bidual, so it's a bounded linear transformation that acts on linear functionals on x. This is because of the property of k, right? Good. And since x is reflexive, you know precisely how this element L looks like, right? It's in the image of the canonical map of x. Okay, so let's write this out. And since x is reflexive, there exists x in x, so that L of f is one of those little j's, jx of f, okay, is f of x for every linear functional on x. This is because the big one is reflexive, all right? But in fact, we claim that this element x here is already in the subspace y, but in fact, x is in y for if x were in the complement of y. Now, of course, Hahn-Banach comes back at you. So you have a closed subspace, you take an element in the complement, then one of the corollaries of Hahn-Banach allows you to construct functionals with certain properties, right? So that's what we're using here, in and out. Okay, then we can find, that is Hahn-Banach consequence, that we can find linear functional on the whole thing, which vanishes since I use this restriction here. So its restriction to the subspace is identically 0, but at that designated point it does not vanish. Okay? Yeah, but this contradicts the following chain of equalities. So we have on the left g of x, which is different from 0 by consequence of Hahn-Banach. This is jx evaluated on g. Now jx on g, this is written up here for all linear functionals, in particular for this little g. It is equal to L of g. But now L of g, maybe with this one, so this equality was the green one, and now this one here is the pink one. This is k f g restricted to y. Yeah, but g restricted to y is apparently the 0 functional, and since this k is in particular linear map, it maps 0 to 0, right? So you got the fantastic contradiction here that 0 is different from 0, right? So that's why that element x actually has to be in the subspace y already. Okay, good. So let's define it as y. Let's just relabel it as y. Is an element in y, and we have that jy of f is equal to L of f. This is the green stuff again, green. And then L of f, this was written up there in pink. It is equal to k. And now f restricted to y. Yeah, but if I write this equality for all f that are linear functionals on y already, then I don't need the restriction for all linear functionals on y. Right? But this is precisely what we wanted, that our k of f is equal to some j sub y. Right? That is it. Okay. So it has the canonical map on y with y sending to j sub y is surjective. Okay, and hence by definition the subspace reflexive. Okay, now next part, moving ahead. If so this is now about the isomorphic Banach spaces. So first, suppose you got two Banach spaces x and z, and they're isomorphic, so there exists an isomorphism. Is an isomorphism. Okay. Then remember we studied the dual transformation early on, so now this comes in really handy. Because one of the properties of the dual transformation, this is the guy which goes between the dual spaces but in reversed order. If the initial one is invertible, then so is the dual linear transformation. So that a to the power t, or the transpose, then so is its dual. I'm missing a word here. Then so is its dual, and likewise its dual again, right? So now you go, this dual here is the dual transformation. So you take the dual transformation of the dual transformation, right? So you look at AT and then the dual of that, which is now a bounded linear transformation between the bidual spaces x star star and z star star. All right, good. Now we need to show that, well, the z star star, or that z is reflexive, right? We suppose that x is reflexive. Now we want to show that the Banach space z is reflexive. So I have to take an element L in the bidual and show that it is in the image of the canonical map on z, right? That's the goal. Okay. So and set element k, which will be, okay, so this needs some trickery. When I wrote this proof, it also took me a while to figure out how to define these elements. So this is one way how it works. So you take L, which is an element in Z star star, and then you compose it with the inverse of the dual transformation of the dual transformation. So that is sent to, that is an element in the bidual of X. You can just check how these maps are defined, okay? But since you know something about the bidual of X, because X is reflexive, and there exists X in X such that K is equal to J sub X with the usual J sub XF is equal to F of X for all linear functionals on X. Okay? In turn, this allows us to define an element Z, which is A of X in Z. Okay, that is it, and that more or less will do it. I've already spoken for 26 minutes, so these proofs are fairly technical, so I want to give a short break. We will finish up this proof early on in the next video. After that, there will be one big theorem about reflexivity of a Banach space and how it relates to the dual space. Is it reflexive or not in that case? And once this is done, then we will have enough theory about dual spaces assembled so that we can finally look at examples and compute concrete dual spaces. All right, that's the plan. I'll see you soon.